Electromagnetism.
I am the first voice you hear.
And I'm the second voice you will hear.
And I'm the third voice, okay?
And I am the fourth voice you will hear. And today we're going to be talking about Transformers. This Transformer, but this Transformers.
Yep, these are the topics we're gonna be talking about today. You can just read them off. I'm not gonna read because I'm lazy. Like you should watch it. Come on, watch it. We animated this. Just watch it. Right? I'll give you time. So, how's your day? I'm sure it's been great, you know, watching us. Yeah. Not the best group, I would say. Right guys?
What's up guys, now I'm going to be talking about the setup of a transformer and its principle of operation. So the setup of a transformer is relatively simple. It just consists of a soft iron core with two coils of insulated wire wrapped separately around it, each coil having different number of turns or loops depending on whether it's a step up transformer or a step down transformer. So by using DC as our power supply, we are actually unable to light up our output, but if we were to use AC as our power supply, now that's a different case. By using AC as our power supply, we are actually able to light up our output because changing current and changing magnetic field is produced, whereas DC does not produce these because it only allows us to get constant current and constant magnetic field. Therefore, it fails to power up the secondary coil. And based on this, we know that a transformer's operation is based on Faraday's first law of electromagnetic induction, which states that any change in the magnetic field of a coil of a wire will cause an EMF to be induced in the coil. This is called induced EMF, and if the circuit is closed, the current will also circulate through the circuit, and this current is called induced current. So this is how it works by electromagnetic induction, and it only works with AC current. The current passes into the primary coil, which produces an alternating magnetic field in the iron core because of its power supply being alternating current. So this alternating magnetic field induces an EMF into the secondary coil, and this allows potential difference to flow across the secondary coil, producing this graph shown in above. So there's a formula we can actually use to find out the potential difference across these cells, and it is voltage in secondary coil divided by voltage in primary coil equals to turns on secondary coil divided by turns on primary coil. In short, Vs over Vt equals to Ns over Np. So for example, basic transformer of 50 volts and 3000 turns in the primary coil, 100 turns and unknown volts in secondary coil. So to calculate the unknown volts, we can actually rearrange the formula, and the answer will be 1500 volts. Now, transformers are almost 100% efficient, so we can assume that power input equals to power output. Vi equals to Vi, but only secondary and primary. For example, 60 ampere and unknown volts on the primary coil, 3 ampere and 15 volts in the secondary coil. So rearranging the formula, we will get the answer of 0.75 volts.
Today I'm going to be talking about back EMF. Alright, so before that, what is EMF? EMF is also known as electromotive force, which is the voltage that is created by any source of electrical energy such as a battery or a dynamo. It is basically the electrical potential for a source in a circuit. Back EMF, however, is the electromotive force that travels opposing the current that induced it. The back EMF is always less than the applied voltage, V. According to Faraday's law, it states that the magnitude of the induced current is affected by the rate of change of magnetic flux as well as these components. Lenz's law states that the induced voltage will oppose the driving voltage. For example, if a change in magnetic field of current A induces another electric current B, the direction of current B is opposite that of the change in current A. Today, I'm going to talk about the energy loss in transformers. Okay, first up is eddy current loss. What is an eddy current? When an alternating magnetic field is applied to a magnetic material, an EMF is induced in the material itself according to Faraday's law. Since the magnetic material is a conducting material, the EMF produced will also circulate within the body of the material. These circulating currents are called eddy currents, and they occur when the conductor experiences a changing magnetic field. These currents produce a loss known as eddy current loss, which are present in transformers. How do we overcome this? We can split the solid core of the transformer into thin sheets called laminations. This reduces the area that which current is being passed through, thus the eddy current loss is reduced. Now I'm going to talk about hysteresis loss in transformers. Okay, what is it? This loss is the consumption of electrical energy due to the reversal of magnetization in the transformer core. This is because when an external magnetic field is removed from the transformer is still magnetized. To neutralize this, some energy is required to be applied. Thus, the loss of energy is present. Hysteresis loss increases the temperature of the magnetic material.
One of the most important uses of mutual induction is the transformer, a device which alters the voltage and current of an AC electrical flow. Now I'm sure you're wondering what the purpose of a transformer is, and the purpose is to raise or lower voltages and currents in an electrical circuit. In today's modern electrical distribution system, the transformers are used to boost voltage levels to decrease line losses during transmission, and I mean the transmission of electricity. And how is it we're getting enough electricity and safely? Transformers can send electricity long distances over high voltage transmission lines, and they are known to do this while minimizing and reducing energy losses during transmission. How this works? When a current flows through a wire, some energy is lost as heat. The higher the current, the more power is lost. And this goes by the formula P equals to I squared R. Step-up transformers at power stations produce very high voltages needed for transmission lines, as high voltages improve efficiency by reducing power and also heat losses in power lines. This although also requires a step-down transformer, as high voltages are too dangerous for use in homes. Therefore, a step-down transformer is used to reduce voltage to safe levels. Anyways, this is simply not the only purpose of a transformer. Transformers are also used as regulators for televisions, refrigerators, computers, air conditioners, and many more. Similar to transmission lines, in air conditions, A step-down transformer is used to step down the voltage from a line voltage to safer and more efficient voltage for use. Step-down transformers can be 120 volts to 24 volts or 240 volts becoming 24 volts. There are many other combinations. Also, radio frequency circuits, which are needed for telecommunications, use air core transformers as it has windings wrapped around a hollow tube, as the picture shows. Radio transformers have tapped windings or two or more windings designed to transfer radio frequency energy from one circuit to another by means of magnetic field. This transformer may have an air core or some form of ferrite core.
Alright, so now I'll be talking about modifications on transformers. I'm Zakai. Yeah, but before we start to roll out, I'm gonna talk about my random thought that I just had. If the early bird gets the worm, the early worm goes out to die. It would mean that we will want to stay in and sleep more, so yeah. So first we can laminate the iron core. Here we can see a transformer with iron cores laminated. So why do we do this? Firstly, we can use it to reduce the eddy current. What is eddy current? Well, you guys should know, because I don't know. Yeah, that's a problem for you guys. Ha! Right. So secondly, we can also reduce the heat loss to surroundings, because the laminate, it is a heat insulator, which makes it harder for heat to escape. And then we can, because of this, the efficiency of the transformer will increase. Yay, efficiency! Yay, not like us students. Yay! So 2, submerging the transformer. So what is transformer oil, you may ask? Well, transformer oil, or insulating oil, is an oil that is stable at high temperatures and has excellent electrical insulating property. It is used in oil-filled transformers, some types of high voltage capacitors, fluorescent lamp ballasts, and some types of high voltage switches and circuit breakers. Okay, so this will make the transformers last longer. If you can make man last longer, because transferring heat into water is easier than transferring heat into air, because particles and all. Yeah. Alright, so this is what I'm drawing now. It is an auto transformer. Why is it like this? Let me just explain it now. It is cheaper than an EI transformer or the normal transformer we see, because it uses less materials to create, also making it lighter. So how this works is that in the primary side, there'll be both terminals attached to it, supplying power, and because the coil on the primary side has more coils than the secondary side has in contact with, because based on the picture, the number of coils affects the voltage produced. Alright, so now there are some fun facts. So if all eagles are sick, then America will not have their signature animal anymore, because America will have to deport all of the eagles because they are illegal. Save me. Okay, so the last one I'll be talking about today will be toroidal transformers, which is a circular transformer, donut shape, which is the best shape because donuts are amazing. It is more effective than a traditional transformer because of its symmetry. The leakage flux is low and radiates less electromagnetic interference, commonly used in power supplies, amplifiers, etc. It is a closed loop core. Magnetic fields are contained within the core, which make it denser, causing the cutting of magnetic field to be more effective. Because of this, it can be a smaller size, which makes it lighter. And that is all for my part. We all just hop on to the next part.
Yo, sup guys? Now I'll be talking about the future modifications of a transformer, right? So, we have 2 ideas that we would like to propose, and both of the ideas actually are based on the same concept, and which is Hellback array arrangement concept. So, before I explain the 2 ideas, I will just briefly touch on this concept. So to understand this, we will have to look at a simple magnet, the arrangement of a simple magnet. Okay, so as we can see here, North Pole, North Pole, North Pole, and down here will be South, South, South. So the magnetic field lines will be drawn in this way, always north to south, right? Okay, but if we use this arrangement, this Hellback array arrangement, we will get something like this. As you can see, all the polarities of all magnets are different. So what this does is actually it concentrates an even stronger magnetic field towards one direction. But the catch is, on the top layer, the magnetic field here being produced here is actually very small. Actually about 1% to 3%, right? Okay, so now that you have a brief idea about this concept, these are the two ideas that we are actually proposing. Okay, so the first idea is this. As you can see here, this is actually a held-back array arrangement magnet. Two of them actually, and this is what is our primary coil. Our secondary coil, sorry. Okay, so for this to work, we will be rotating this held-back array arrangement at really high speed. Because what this does, as it rotates at really high speed, its magnetic field is constantly changing, constantly alternating. So what we're getting? Alternating magnetic field. So this alternating magnetic field would actually induce an EMF into our secondary coil. Same goes to the other side. So both sides will be inducing its own induced EMF into the secondary coil, and this will power our output. So this is really good because we don't even need our basic transformer, our power supply, which is AC anymore, because we can just rotate this held-back array arrangement at really high speed, and we will already get that alternating magnetic field. Not by using this alternating current to get that changing magnetic field, because the current, the direction of current is different every time. So this is the advantage. So at high speed, changing magnetic field increases, rate of change of magnetic field, which is just this time, magnetic field increases, and rate of induced EMF in the secondary coil increases. Right? So second idea is basically the same. So what you can see here is actually a cylinder of layers, made out of layers of our held-back array arrangement magnets. So from the top view, it actually looks something like this. This is our magnet, our magnets, different polarities at different direction, and it all concentrates its magnetic field towards the center. And what's in the center is actually our secondary coil. So just like the idea, our first idea, induced EMF will be produced in our secondary coil, and this will light up our output. So that's basically how it works, right? Okay. So there's actually a formula that we can use to calculate this magnetic field being produced at this part of the held-back array arrangement. Not this part, because at this part, magnetic field is like almost zero, just 1% to 3%, really small. So this is the formula: Fxy equals to Fo e power of I kx times e power of negative ky. So Fxy is actually our magnetic field that we're producing here in terms of Fx and I Fy, and I is actually an imaginary number. So Fo is actually our magnitude of the magnetic field at the surface of the array. So this part, the magnitude. And lastly, our K is our spatial wave number. So that concludes our two modifications we would like to propose. And thank you guys. Peace out.
Alright, if you made it to the end of this video, we'd like to thank you for watching it. We'd also like to thank Mr. Anand for endorsing this video. Mr. Anand, you a G.
MVP.
Okay, with that said, we're gonna end the video now. Alright, thanks for watching, and we'll see you in class. Oh man, guys, it's finally over, man.
Transformers, what a joke.
That's so much of my time. It's such a waste of time, honestly.
Exhausted.
How much marks? 10?
I don't know, man. Let's go get good prep.
Yeah, let's go.
Cool. Alright, it's on me. Let's go.
Let's go, guys.
Yeah.